This is lecture number 10 of the course AU 203 Statistics and Quality Control, and in this lecture we will talk about conditional probability concept and its formal definition, mathematical definition of conditional probability. Then we will go into the law of total probability, and then in the end we will go into the Bayes theorem, which is based on the conditional probability concept. Okay, so let's say you have an ordinary 6-face dice and you are going to roll it one time. So what are the possible outcomes that are in that experiment are possible? So either you get 1 on the dice, or 2, 3, 4, 5, or 6. So this would be your sample space, and we represent by a set S as the sample space. Okay, we are interested in what is the probability that in an experiment 2 is rolled. So according to the definition of probability, we know 2 is will happen one time. So the probability of getting 2 in that experiment would be 1 out of 6. So favorable outcome is 1 and total possible outcome is 6. So the probability of getting 2 once you roll it down one time, and obviously not for 2 but for any digit, the probability is 1 by 6 once you throw a single 6-face dice. Okay, let's say we have some more information given, and our dice is come up with some even number. So what will be the reduced sample space now? So our reduced sample space, we call it as R. R means reduced. So if you're interested in even number, or die came up with an even number, then the possible sample space would be either 2, 4, or 6. Okay, now given that the number rolled which is not odd but which is even, then what is the probability of getting 2 this time? So this experiment is different from this experiment. In the previous experiment, we have a sample space S having 6 elements, and the probability is 1 by 6 to get 2 on the dice. But now we are interested in only, we additionally know that during experiment the number that has come is an even number. So your sample space is now comprising of either 2, 4, or 6. So what would be the probability of getting 2 is, so here for this reduced sample, we write the probability of getting 2, and we have this vertical bar which represents that such that, or given that the number is even. So we have some prior information that number that is going to come, because we are doing an experiment and it's a random experiment, so any number can come in. But here you have some additional information available. The additional information is that the number would be an even number. So now the favorable outcomes is 3. Total possible outcomes are 3, and out of that favorable outcome is getting 2 on this dice would be 1. So 1 upon 3 is the probability. So these two experiments are different, because in the first experiment your probability is 1 by 6. But once you have some additional information is known, then your probability has increased. So this is actually the idea behind this probability. We call it a conditional probability, because we are calculating the probability of getting 2 on the dice, but we have some additional information that your number is even. So once you know that your number is even, then the probability would be 1 by 3, which is higher than the probability once you have 6 possible outcomes where you don't have any additional information. So once you provide some information, so this probability would be called as conditional probability. Okay, we generalize this concept of conditional probability. Let's say we have two events A and B, and obviously the probability of event B is not zero. Because if it is in the denominator, then this probability, conditional probability, would become undefined. Then we can say that the conditional probability that the event A occurs such that, or given that B has already occurred, is denoted by this notation, that the probability of event A, this symbol represents given that B has already occurred. So at this time our sample is a reduced sample. For example, in this sample space you have two events A and B, and A intersection B is the common portion between A and B. So once we are interested in calculating the probability of event A, that element is from event A, and given that B has already occurred, so it means our sample space is now reduced. So the probability would be equal to, we can write the probability of event A given that B has already occurred would be, we are interested in event A. So in this sample, which is only comprising of set B, the number of elements that is present in A and B both would be actually in the numerator, because we are interested in calculating the probability of event A. So other event A means it must be from event A. So that is actually representing this common portion. And divide by the number of elements present in the sample space. So now we have a reduced sample space. So now we have a sample space of B only. So that's why it is in the denominator B. So we can represent the conditional probability of event A given that B has already occurred would be equal to the number of elements that is present in A and B divided by, which is obviously smaller than the number of elements present in B. So number of elements present in B would be a bigger number, and number of elements which are present in both A and B would be a smaller number. So that's why always the probability lies between 0 and 1. So this would be this type of probability would be called as conditional probability. So we are forcing some condition that we are interested in calculating the probability of event A. We have some prior information. We know that B has already occurred. That probability would be equal to the number of elements in both A and B divided by the number of elements in the sample space. And now the sample space is only the set B. If you divide this numerator and denominator by the number of elements that are present in the sample space, so the numerator would be representing the probability, denominator also would be representing the probability, and we can write that. So it would be the probability of event which is common in both A and B divided by the probability of event B. So that would be the formula for conditional probability. So here probability, it should be read as the probability of event A we are interested in, given that B has already occurred. It means we are interested in the probability of event A when your B has already occurred would be can be calculated by knowing the probability of event which is both A and B, and dividing by the probability of set event B. So this would be the formula for this is the formal definition for conditional probability. And we know that the sample space has been a reduced sample space. So denominator is some smaller number, then this conditional probability would be some higher value. Compared with if your sample space is the whole sample space. This time the set B is become your reduced sample space. Okay, so we can write the same equation like this also, because this numerator, if you multiply it by this thing, we can say that the probability of A and B would be equal to the probability of A given that B has occurred multiplied by the probability of event B. So this is how we can write down. As we know, either we take a common between A and B or the common between B and A. It does not make any difference because the number of elements which are common in A and B is actually the same as number of elements which are common in B and A. So that is using that property, we can say that the probability of B intersection A, or the common between B and A, would be, we can write like this. That would be the probability of B given that A has already occurred, and multiply by the probability of A. So if we compare these two things, we can use, because this intersection is this and this intersection is this, both are identical, then we can say then this side would be equal to this side. And this rule is actually called as multiplication rule. So where what we are interested in on the left hand side, we are interested in calculating the probability of event A, whereas we have an information about event B. And here we are interested in knowing the probability of event B, whereas the event A has already occurred. So these two would be equal according to this equation, and this is from the definition of the conditional probability, and using the fact that the probability of A and B and A are exactly the same. So this result into this equation, and this rule we call it a multiplication rule. And we will solve using that multiplication rule, we will solve problems related to that. Okay, so just consider a manufacturing process where 400 parts are classified by surface flows and defective. So altogether you have 400 parts, and 10% of the part contains visible surface flows, and visible surface flows means the 10% of the 400 would be 40. So 40 parts are having surface flows, and 25% of the part with surface flows are defective. So it means out of that 40, the 25% of that 40 would be 10 parts that are having surface flow as well as defective. And here additional information that is given is only 5% of the part without surface surface flaws. So there are only 5% of the part without having a surface flaws. So there are 5% of the 400 parts would be having no surface flaws. And this information is 5%, only 5% of the part with surface flows are defective. So only this information says that 5% of the part with having a surface flaws. So 440 parts have surface flaws, and only 5% of the parts which have surface flows are defective. So they are actually 18 is that number which is having no surface flows, but they are defective. So horizontal row represent a defective part and vertical row represents surface flows, whether it has a surface flow or it doesn't have a surface flow. And the horizontal says it has a defective part and it doesn't have a defective part. So if you add them 10 and 30, it would be 40. And if you add them horizontally, you also get the total. So once you add them, these two together, it would be 400, or if you add them together, it would be 400 altogether. So what we are required to find out is the probability of a defective given that having a surface flaws. So it means this statement says that we are interested in calculating the probability of defective part. And we know the total defective parts are 28 out of 400. But here the additional information is given that we are required to calculate the probability of a defective part once you have some condition that such a defective part is having surface flaws. So there are only 10 parts that are defective and having surface flaws. So first we will write down define events. For example, D is the event we have defined as when your part is defective, and event F is defined as the part having surface flaws, and F prime is F naught, or F prime is we use a letter to represent having no surface flaws. So using that notation, we can write down the first part, that what is the probability of a defective part given that having a surface flaws. So we directly from the table, one of the way is directly, because these are the 10 number of parts which are defective as well as having surface flaws out of total 40 parts which have a surface flaw. So this conditional probability we have calculated directly would be 0.25, or we can do it using the formula for conditional probability, which says that the probability of a defective part given that which is from surface flaws would be equal to probability of the intersection between the defective and the surface flaws divided by the probability of the parts which has flaws. So total parts having flaws, surface flaws, are 40, which is yes. So 40 out of 400 would be the probability of getting surface flaws, and 10 is that number which is having an intersection, having a surface flaw as well as defective out of 400. So 400 and 400 cancels out, so you got the same thing. So once the information is given in the table like that, so you can evaluate the condition probability directly, or you can use the formula to calculate that conditional probability. So either way you can do that. Okay, similarly in the next part, what is the probability of getting a defective part given that having no surface flaws? So in the language of conditional probability, we can write the probability of getting a defective part given that having F prime means no surface flaws. So there would be, if you do it directly, then you have 18 which have no surface flaws and which are defective. So 18 out of 360 would be your this conditional probability. Or if you use an alternative method, which is the formula for calculating the conditional probability, you will use that the probability of getting a defective once you know that that doesn't have the surface flaws would be the probability of intersection of defective and having no surface flaws divided by the probability of not having a surface flaw. So probability of not having a surface flaws is altogether 360 out of 400 would be the probability that you have no surface flaws, and the common portion would be out of 400 would be 18. So you got the same 0.05 is 5% is the probability that you pick a part which is defective, and we already know that that part has no surface flaws. So 5% would be the probability, and the probability of getting a defective part given that it has a surface flaws would be some higher probability. 25% is this probability. And the same situation we can represent in this diagram as well, where we say F is the part having surface flaws and F prime is the part without a surface flaws. And we can see this this conditional probability 0.25. 25% is the part which is defective and having surface flaws, and 5% is a very small fraction of the part which is defective and having no surface flaws. So that is a small number. So this area dash this shaded area represent this probability, and this bigger shaded area represent this probability. And we can represent the same situation on a tree diagram as well. For example, the first thing is to check whether it has a surface flaws, yes or no. So there are 40 items having surface flaws out of 400. So 40 over 400 would be the probability that the part has a surface flaws. Or if it doesn't have a surface flaws, so 360 out of 400 having no surface flaws. Okay, if a part has a surface flaws, then the second thing is whether it is defective or not defective. So we know there are two possibilities and there are 40 parts which are actually having a surface flaws altogether, and 10 is having a defective. So we know that it has a surface flaws, and then we need to use a multiplication rule or AND rule. We know that there is a surface flaws, and then it is to be defective. So there's 10 over 40 would be that probability, and 30 over 40 would be the probability if it is having a surface flaws and not defective. So that would be 30 over 40. Similarly, if it doesn't have a surface flaws and it is defective, so it means no surface flaws but defective, it would be 18 by 360 altogether. Or so we can represent the same situation either in the form of a table or some visual graphical representation, or in the form of a tree diagram. All are representing the conditional probability concept. Or sometimes the problems are given in the form of such tables, like we call it a contingency tables. For example, here a contingency table for age and the rank of the faculty member at a university is given. Suppose we pick a faculty member at random, and we are interested in what is the probability that the selected faculty member is in his or her 50s. So if you look at the table, so these are the full professors, these are associate, assistant, and these are instructors. And A1 is actually representing the R1, R2, R3 representing the rank, A1, A2, A3 representing the age group. So under 30, there are 2 full professors, 3 associate, 57 assistant, and 6 instructors. And in the age between 30 and 39, there are 52 full professors, 170. So altogether, there are 402 faculty members in this age group. And under 30, there are 68. And altogether, there are 1164 faculty members. So in the first part, what is given is to calculate the probability that you pick one faculty member out of 1164. You pick a 1, and that member would be in his 50s. It means 50s means in this A4 range, where between 50 to 59. So there, how many people are in this range? 253 people are in this range. So the first we define just like an event A, which is the faculty member is in 50s, and event R is that it is assistant professor. So first part is very simple because we are interested in the event in which we have only that faculty member should be in his or her 50s. So A is the event which is in her 50s, and in 50s there are only 253 out of 1164. So this is the simple way to calculate the probability, and we called here is because there is no condition mentioned, that's why it is called as unconditional probability. Let's say for part B, what we need to know is we have some additional information. We need to calculate the probability, because I have deliberately mentioned here unconditional and conditional, but in exam what would be written is just the probability to calculate when selected faculty member is in her 50, given that, so this is a keyword which gives you the signal that this is the conditional probability, given that is an assistant professor is selected. So in the language of probability, you write probability of getting event A. Event A means that faculty member would be in 50, given that that faculty member is in the rank of assistant professor. So there are, if you see rank 3, that would be 320 assistant professor, and out of 320, the 36 are in this age group. So that conditional probability would be 36 by 320. So this is how you can calculate this conditional probability. Or you can use the formula for calculating the conditional probability, that the probability of the faculty member is in 50s, given that its rank is assistant professor, would be probability of A intersection R means in 50s, as well as in so this probability you can work out by calculating the common between age and rank. So it would be 36 divided by 3 out of 1164 total, and the probability that it is in the rank of assistant professor, the 320 out of 1164 are in the rank of assistant professor, so this cancels out, so it is exactly the same thing. So 11.3% is the probability that so what we see here is once you apply this condition, then you have some additional information, and this probability is different from this probability. Depending upon the numbers, the value would be different. Okay, so now we move on to the concept of law towards deriving law of total probability. So we have got the understanding of conditional probability. Let's say we have a sample space comprising of three events, A1, A2 and A3. So the total number of elements present in A1, in A2 and A3 would be equal to the number of elements in the sample space. So we can say that A1, there is nothing common between A1 and A2, nothing common between A2 and A3. So we can say that they are mutually exclusive, and the sum of the elements present in these A1, A2 and 3 makes up a sample space. So without any overlapping, once it is an overlapping, then there won't be called as mutually exclusive. So here it is a special case where it is mutually exclusive as well as exhaustive. So once it is exhaustive, we can write divided by number of this equation. If you divide by number of elements in a sample space, so if you divide by this, you are going to get 1 here, and this would be the probability of event A1, A2 and A3. And we can think of A1, A2, A3 are actually the subgroup of the sample space, or sometimes they are called as partition of the sample space. So what we have done is the whole sample space is divided into 3 partitions, A1, A2 and A3, partitions or subgroup, whatever you call it. Okay. Now we bring up another event. We have given a name called B, and B is placed such that some part is common with A1, some part is common with A2, some part is common with A3. So in this sample space, which is comprising of 3 events, A1, A2 and A3, we have brought another event B in such a manner that there is some part with A1, some part with A2 and some part with A3. So we can say that the elements B comprising of the union of the common between A1 and B, A2 and B, A3 and B. So if you add them together, you will be going to get the number of elements present in set B. Its probability we can write like that as well, if we just are not going into the same notation but directly writing down that the probability of event B would be equal to the union of all the intersections with set B and the partitions. So I can write this, and you know this union symbol means OR. So OR can be replaced with addition symbol. So this common and or this common or this common. So OR is replaced with addition symbol here. As you know, AND is for multiplication and OR is for addition. So this same idea, if you have 3 partitions, you can write like that. If you have k number of partitions or portions, then you can write that the probability of B would be nothing, the probability of the common between A1 and B, A2 and B, A3 and B, A4 or AK and B, up to k number of partitions we can do. Okay, so this can be written in a simple sigma notation like that, which is actually the sum of the probabilities of the partitions and the event B, which is common. If you take the sum, that would be equal to the probability of event B. From this conditional probability multiplication rule, we have already seen that the intersection part is can be written either in this form or this form. So what we do is we write down this thing with using that law, that probability of B given that A1 has already occurred times the probability of A1 plus the probability of B given that A2 has already occurred, and so on, so on. So this would be called as law of total probability when you have there is an event A which is having not A, but there is a sample space which is comprising of event A1, A2 to up to AK, and then you introduce an event B which has something common between the event B as well as with all these partitions. So the probability of event B can be calculated by just summing up these conditional probabilities. And obviously this law of total probability would be valid once you have a sample space is such that where A1, A2, up to AK are the mutually exclusive and exhaustive events. And then we can work out the probability of event B in such a manner that the probability of event B can be calculated using this definition of conditional probability. Okay, now let's see how we can use this law of total probability in solving the problem. There is a worker operated machine that produces defective item with the probability of 1%, that is 0.01, if the worker follows the machine's operating instruction exactly. So once your worker is very good and it observes the operating manual and the probability of getting a defective part once the worker use the operating instructions completely, then its probability is only 1%. And with the probability 0.03 if he does not. So if the worker does not follow the operating instruction, the probability of getting a defective part is higher, which is 0.03 is the probability. Okay, if the worker follows the instructions 90% of the time, so you have some information that 90% of the times worker follows the instruction, and so what we have to calculate, what proportion of all the items produced by the machine will be defective. So all the items produced by the machine will be defective. So here we have to make symbols. Let's say event I is when worker follows the operating instructions, and I prime or I complement is when worker does not follow the operating instructions, and event D is when your item produced through that machine is found defective. So what information it is given here is this probability, what is given here is actually a conditional probability, because this is the probability of getting a defective item given that worker follows the instruction, and this is the probability of getting a defective part when worker is not following the instruction, which is somewhat higher than when it follows the instruction. And second information that is given is probability of following the instruction is 90% of the time, and probability of not following the instruction is 10%, that is 0.1. So by using the law of probability, we can say that the probability of a defective item is just multiplying the conditional probability, summing up the conditional probabilities. So probability of defective given that it is following the instruction times the probability of following the instruction plus the probability of getting defective given that not following the instruction times the probability of not following the instruction. You substitute the values, because this thing is 0.01 and this thing is 0.9 plus 0.03 into 0.9. 1. So you can think of actually the probability of getting a defective part here is not just the probability, the sum of the probability, but is actually this becomes a weighting function. So this conditional probability becomes a weighting function. So this probability of getting a defective part in that scenario would be 1.2%, because what proportion of the items produced by the machine will be defective. So all the items, so we are interested in the total probability that the probability of getting a defective item would be equal to the sum of these probabilities. Okay, we can use this same law of total probability for this particular type of problem as well. Here we have three machines which are used to make a part in a factory, and we have some information given. For example, machine 1 makes 60% of the parts, 60% of the parts with machine 1. So you have one part which you can make by three different machines. And 7% of the parts would be defective if you make from machine 1. Machine 2 makes 30% of the part, and the probability of defective is 15%. So we can think of machine 1 is the newest machine and the advanced machine, and what we want is most of the part, 60% of the part, to be produced from machine 1, and the percentage of defective is low. And machine 2 is an older machine, and machine 3 is the oldest of the machine, which you are only asking 10% parts to be produced, and 30% of the times it produces a defective part. So what we are doing is a part is randomly selected. What is the probability that it is defective? So from this scenario you should understand that we are dealing with the law of total probability. So first you define that event M1 is part coming from machine 1, M2 is part coming from machine 2, or M3 is part coming from machine 3, and event D is when your part is defective. So the first information that is given is your part comes from your machine 1, it is 60%. Part coming from machine 2 is 30%. Part coming from machine 3 is 10%. And second information that is given is you know that the part is defective, as you have some additional information that this 7% would be the probability when the part is defective, but it has been produced from machine 1. So we can say that the part is defective given that it is produced from machine 1, which is 7%, that is 0.07. And similarly 15% or 0.15 is the probability that part is defective, and given that this part is coming from machine 2. Part is defective given that the part is coming from machine 3 would be 0.3. So you know all these conditional probabilities and this weighting functions. So according to law of probability, the probability of getting a defective part would be equal to, because you have your probability for each machine is different. This is 7%, this is 15, this is 30. So once you randomly pick, and what would be the probability that part is defective? So using this law of total probability you can work out. So just substitute all the values given here, and neither 7% nor 15 nor 30. So this weight, due to that weighting, the probability of getting a defective part is 11.7%, higher than 7% but lesser than 15 or 30%. So that would be that is where you are going to use this law of total probability. And you can think of a superset is having or sample space is having parts produced for machine 1, parts produced for machine 2, and parts produced for machine 3. So 60% you are producing for machine 1, and 30% you are producing for machine 2, and 10% you are producing for machine 3. And what you are interested in bringing up an event called defective part. So there would be some common area where we can say that there would be an intersection of this part, and that would be the part which is defective and produced from machine 2. This would be the part which is defective and produced from machine 1. This would be the part which is defective and produced from machine 3. So I have used this Venn diagram to represent that scenario, or you can represent the same scenario using the tree diagram as well. So okay, then the last thing in this lecture is Bayes' theorem. So we know the conditional probability definition that the intersection of A and B would be either this or this. They are same thing. Either you write like this or you write like this because of using this multiplication rule. Or you can say that the definition for knowing the probability of A, given that B has already occurred, so would be equal to probability of B given that A has already occurred times the probability of A divided by the probability of B. And obviously this equation is valid only when the denominator is not 0. So obviously the probability of event B would be always greater than 0. It cannot be equal to 0. Okay. What actually this Bayes theorem is all about, for example, on the left hand side we are interested in probability of event A, where information about B is already given, and here we are interested in probability of B where information about A is already given. So this is something prior information, this is something we are interested in afterwards. So we call it a posterior probability, this is we call it a prior probability. And this would be your evidence actually for getting this probability of event B. Okay, we will use the formula to generalize the same thing. Instead of two events A and B, you could have E1, E2, E3 and Ek events, and then there is a event B which is common in with event 1, with event 2, with event 3. So according to this probability of event 1, given that B has already occurred, so this would be the probability of B, and using the law of total probability we have written this denominator, and this would be our numerator. This is actually the same thing. So we are interested in the probability of B given that event 1 has already occurred times the probability of event 1, and the probability of B is actually the probability of B written using the law of total probability. This thing which is in the this event which is written here is, for example, on the left hand side, it is actually we call it a posterior probability. Post means after. So it means we are interested in the probability of event 1 given that B has already occurred. It means event 1 or event K is always considered after event B. It means event B has already occurred and we are interested in calculating the probability of event 1 or event 2 or event K. So that's why this left hand side is called as posterior probability. And this probability is probability of getting for event B where we have an information that event E1 has already occurred. So it means event 1 or event 2 or event K is actually considered before the event B. It means event 1 has already occurred and afterward B is going to occur. So that's why it is called as prior probability. And what the Bayes theorem is, this posterior probability is linked with this prior this probability, what you call it, a prior probability, and this is something posterior probability. And the Bayes theorem is actually the relationship which link between these two type of probabilities. And Bayes theorem can be visualized in different way like that. For example, according to the definition of conditional probability, H is some our assumption or hypothesis, and E is the evidence which you gather using the measurement. For example, we are interested in calculating the probability of event H, which is our assumption, given that we have certain evidence, would be equal to the probability of event E given that H has already occurred times the probability of an evidence divided by probability of your hypothesis and divided by the probability of your evidence. We can write down this term is as posterior probability this term as a prior probability, and this thing is our evidence, or we call it a marginal likelihood. In the language of statistics, this evidence is sometimes called as marginal likelihood. And this would be the probability of event A given that H or hypothesis, our assumption has already occurred. So this is something, the likelihood. Or we can write like the same thing, we can write like this: instead of evidence is collected through data. So E is just replaced with data, the rest of the thing is actually the same. So this would be my prior probability, this would be my evidence which comes from my data or some measurement. Or we can say that Bayes' theorem is nothing, just linking posterior probability with prior probability through likelihood and evidence. So we can think of Bayes' theorem as something on the left hand side which is posterior, which is unknown, and if you have a prior knowledge, and if you have evidence, and if you have a likelihood probability, you can work out that posterior probability. And Bayes' theorem is nothing, a relationship which link prior probability with posterior probability. And one can think of, visualize the Bayes' theorem like that. For example, there are two persons having beard and having the problem of eye problem called astigmatic, where your vision is blurred. And there are three people which having no beard but having a occurrence of astigmatic, they have blurred vision. Or there are six people having which has beard but not having this blurred problem, blurred vision problem. Or if you have 9 people which is not beard, B cap or B prime, sometimes we like prime or sometimes like cap, so that has no beard. So altogether you have 12 people here and 15 here and 5 here, so altogether you have 20 people. So we can represent this conditional probability, this would be the probability of having beard given that it has astigmatic. So there are 5 people which is astigmatic, and there would be 2 people having beard. So that would be this probability, and probability of astigmatic would be total there are 8 people having astigmatic, and the probability of astigmatic is 2 people altogether having beard and not beard. 5 people would be astigmatic and total would be 20 people. So if you multiply that together, this one cancels out, so you got the same thing. So this would be the probability that having a beard given that astigmatic. So probability of getting beard given that it is from astigmatic, so 2 divided by this total. So that would be this conditional probability. Or other way around, using this multiplication rule, instead of probability of B, if you are interested in probability of A, given that B has already occurred, and you got the same thing which satisfy this law of multiplication. There are interesting set of problems can be worked out using that Bayes' theorem. For example, this last problem in today's lecture, Mr. Beck is a civil engineer and he is asked to design an overbridge. So it is just a lots of a skyway which connect two buildings. The chance that his design is going to be faulty is 60%. So whenever Mr. Beck design is faulty, he is not a good engineer, so his design is 60% times faulty, and the chance that his design will be correct is obviously 40%. Okay, the chance of the overbridge collapsing, if the design is faulty, so is 90%. So 90% is the probability that your bridge collapse due to the faulty design. Otherwise, the bridge collapse is not because of the faulty, because of this engineering design, but it is because of some other reasons. So 20% is that probability. So the question is, what is the probability or chance that an overbridge built by Mr. Beck will collapse? Or in second part, what is the probability that the design of Mr. Beck was faulty in the light of an overbridge designed by him collapsing? So first of all, we define events. For example, event C is, we define that the bridge get collapsed. Event even is when your design is faulty. Or if it is not faulty, then it is event 2 is when your design is correct. So we can write down the probability of event 1 when your design is faulty, which is 60%, and when your design is correct, not faulty, we can use it even prime as well, but I've just used E2 or any other letter you can use. So that would be the probability of correct design, that would be the probability of faulty design. Okay, the next information that is given is your the chance of overbridge collapsing. It's mean the probability of collapsing the bridge given that the design is faulty. So such that design is faulty would be 0.9. And the second thing, which is 20%, is what is given is the probability that the bridge collapse given that it is correct design. It is 0.2. So the first thing we have to work out what is the probability that the overbridge built by Mr. Black will collapse. So we are interested in the total probability that the bridge is going to collapse. So using the law of total probability, probability of collapsing the bridge would be probability of collapsing the bridge given that it is a faulty design times the probability of faulty design plus the probability of bridge collapse given that it is not a faulty design or is a correct design. So just adding all these, putting up all these probabilities, and you will be able to get. So 62% is the probability that bridge is 60% of the chance that the overbridge designed by Mr. Beck is collapsing. In the second part, as you know, we have what is the probability that the design of Mr. Beck was faulty. So we have some prior information that the design is faulty in the light of an overbridge designed by him collapsing. So what information we are interested in? We have an information of the probability of collapsing is given. So what we need is to work out that the probability of the design of was faulty. So we are interested in the faulty design. So we are interested in the probability of event 1 given that it is collapsing would be equal to probability of collapsing given that it is from due to the faulty design divided by this probability of collapsing, which is the sum of the law due to the law of total probability. So using that Bayes theorem, we will be able to find out that 87% is approximately the probability that we know that the bridge has collapsed and it is due to the faulty design of Mr. Beck. So 87 is this probability that Mr. Beck design becomes faulty and it is collapsing the overbridge. So this is how we need to apply this Bayes theorem, and here I stop this lecture.